couple of weeks ago, we used a determinant called the Wronskian to decide whether k functions are linearly independent or not as functions. Now we're going to use a different Wronskian involving k vectors of functions. So let's review how the last Wronskian worked and then look at how the new Wronskian is going to work. So recall that the Wronskian of k functions, let's call them f1 of t through fk of t, gives us information about whether these functions are linearly independent. So we define W of f1 through fk to be the determinant of the matrix we get by putting f1 through fk in the first row, and then the derivatives in the second row. And then we go all the way down until we have k rows, so I guess that's the k minus first derivative is going to be the last one. So we learned two facts about this Wronskian. One fact is if the Wronskian of f1 through fk is non-zero for some t, then f1 through fk are linearly independent. So they're linearly independent functions. Now if we take this derivative and plug in a value of t and get 0, then we have no information. Now there's a special case of a collection of k functions that it gives us a nicer result. The special case is, let's assume f1 through fk are solutions of the same homogeneous linear differential equation. Then we have two cases. Either one, the Wronskian of these functions equals 0 for all t, and the functions are linearly independent. Or 2, the Wronskian, non-zero means linearly independent, or the Wronskian equals 0 for all t, and f1 through fk are linearly dependent. So knowing that those functions are solutions of the same differential equation gives us a nice test where we definitely make a conclusion. If we don't know that the functions are solutions of the same differential equation, then we have a yes case and a maybe case. That's not as nice. So knowing that they're solutions of the same differential equation gives us a nice test with a yes or a no. No maybes. All right, now Wronski also studied vectors of functions. So let's let x1, I'm going to write bar to emphasize that this is a vector. x2, let's say we have k vectors of functions. And each one has the form, well, it's a vector of functions. So each of the form xi equals some function of t, some other function of t, etc. So the question is, when are these k vectors of functions linearly independent as vectors of functions? So now we define a second Wronskian determinant. Not exactly the same as the last one. So we're going to find a new Wronskian to be the determinant of the matrix whose columns are these k function vectors. So W of x1 through xk equals the determinant of the matrix that has x1 in the first column, x2 in the second column, and xk in the kth column. All right, now we have two facts which are analogous to the facts we know about the other Wronskian. First of all, if the Wronskian of x1 through xk is non-zero for some t, then x1 through xk are linearly independent as vectors of functions. On the other hand, if we take the Wronskian and this is 0 for some t, then we have no information. So maybe they're linearly independent, maybe they're not. On the other hand, we have a special case. Again, if we assume that x1 through xk are all solutions of the same homogeneous first order linear system, of differential equations, then either one, we have the Wronskian being non-zero for all t, and these functions are linearly independent. Or the Wronskian is 0 for all t, and the functions are linearly dependent. So again, we get a nice test with a yes answer or a no answer if we know that these function vectors are solutions of the same homogeneous differential equation, really a system of differential equations. If we don't know where these vectors of functions come from, then we've got a test with a yes possibility and a maybe possibility, which is not as nice as this yes if we get non-zero for some value of t, and no if we get 0 for some value of t. So let's do an example. Since we're studying linear systems of differential equations, I think that the second version of the Wronskian theorem is going to be the one that's most interesting to us. We're going to be taking vector valued functions, which are solutions of the same system of differential equations. So for example, recall that x prime equals (1, 2, 2, negative 2, x). Well, this x prime is really x1 prime, x2 prime, and this x is really x1, x2. Although maybe that notation conflicts a little bit with this notation, where x1 is a vector, and here x1 and x2 are components of a vector. So let me leave it the way I had it first. So x prime equals 1, 2, 2, negative 2x has solutions. So we verified that e to the negative 3t, negative 2e to the negative 3t is one solution, and e to the 2t, 1/2 e to the 2t is another solution. We also verified that all linear combinations of these are solutions, but here's two solutions. So the question is, are these linearly independent solutions or not? So well, we take the determinant of the matrix we get just by putting this in the first column and that in the second column. E to the negative 3t, negative 2 e to the negative 3t, e to the 2t, 1/2 e to the 2t. So that's the Wronskian of these two vector valued functions. And we got e to the negative 3t times 1/2 e to the 2t. So that's 1/2. When we multiply exponentials, we add the exponent. So 2t minus 3t is negative t, minus negative 2 times e to the negative 3t times e to the 2t. Again, we're multiplying the same two exponential functions, so we add what's in the exponent and we get negative t. So that determinant is half of this plus 2 of this. 2 is 4 halves, so 5/2 e to the negative t. Since 5/2 e to the negative t is greater than 0 for all t, then this is non-zero. The two vector valued functions are linearly independent. In deciding when solutions of a linear system are linearly independent is going to be an important part of stating the entire set of equations to that system of differential equations. The end.